Yeah, dear all, good morning. The last class we discussed projection of a vector or projection onto a line. Now we are going to discuss projection onto a subspace or projection onto a plane. Already you know the plane means the plane uh, span a some subspace. Now what the projection? How to project a vector in a onto a plane, onto a subspace or plane. So now just we take any one. That means anything. So this is the plane. It's a subspace. That suppose we take. I'm taking some n vectors. These n vectors are one to whatever n up to n vectors. N vectors are there. That n vectors are generating W. Suppose start with n vectors. Let u1, u2, un belongs to Rm. Be n linearly independent column vectors. Column vectors. These are vectors. These vectors spans a subspace. Subspace W. That is span means W equal to span of these vectors. U1, U2, here U. So now here you are taking this n less than or equal to m. You have taken n vectors. The each components are m components. But you have taken u1, u2, n. That n less than or equal to m. Less than equal m or less than vectors. So now our aim is now find any. Suppose take any vector. Suppose take vector. Suppose I take vector b in Rm. Now I want to find the projection of this vector. Suppose take any one. Suppose I take this one. This is the projecting. This is a projection P up to here. Projection. See now take from V to this projection some dotted line. Already last class we discussed. We are getting some orthogonal. See this is the error vector. We are taking E is already you know V minus P. So which vector are projected? The vector minus projected vector. Yeah, this is the one. See now these are making right angle triangle. Yeah, that projected vector, which vector are projecting that vector and error vector. See now our aim is we have to find this P. How to find this P? So now observe here this diagram. See this U1, U2 all are spanning W. So all vectors are W. These vectors. See now our aim is suppose we are given any vector V belongs to Rm. Suppose we are given Rm. How can what the question? How can we? Our question is how can we project V belongs to Rm onto subspace W. This is the main question. How can we project V to this subspace, this vector? So now in other words you can say can we find a vector? Can you find a vector P belongs to W? The projected vector is also in W also. Can we find P belongs to W such that the error vector E V minus P is orthogonal, or you can say perpendicular to all of W. See, now we can find any vector P belongs to in W, that vector also, such that the error vector is orthogonal to all of W. Write in a matrix or in dot product. That is in a right, that is V minus P orthogonal to, suppose U, for all U belongs to W. If write in the dot, that means V minus P dot Ui for all I is 1 to, how many vectors are there? 1 to n. This one. So now write, this is the V minus P. So now write this inner product. This one you can write Ui transpose into V minus P equal to 0 for all I is equal to 1 to n. See, here is any equations that we are getting corresponding. How many dot products are there? Or inner product n. Any equations are there using dot product. Suppose take this equation 1. Dot product taking using dot or using, you can say, right, involving, here involving see, now here involving n dot products, because each one you get dot product for each UI, for each UI. So now we can do them all at one by setting up a matrix. Suppose we are setting this all dot product, this equation matrix A using the UIs. We are using only UIs as the column. Okay. Using the column subset, that is, suppose I am setting A equal to this matrix. The first column is U1, next second column is U2, and third column is U3, and so on. Our last column UN. Yeah, this one we are setting matrix A. This one U1, U2, UN. Note that each vector, this UI belongs to Rm. UI belongs to Rm has m coordinates. So that, suppose this equation n coordinates, how many vectors are there? N vectors, m coordinates and n vectors. So that A is an m by n matrix. This one. So now it's a m by n matrix. This m coordinates and n vectors are there, m by n matrix. Now if you set up all equations, the set of all conditions what were listed in one, right? Can we rewrite? Suppose can we rewrite the set of all conditions? How many are there? These are n conditions. That means we write this is the matrix. That means we write this one A transpose V minus P equal to 0. The same as you can write, multiply this one, A transpose V equal to A transpose V. Suppose take this equations 2. So now observe here, later. So now take this one. So we need to projected vector. We need the projected vector P. See the projected vector in the W. We need the projected vector to be a vector in W. Since uh, since we are this is a project in W. Since we are projecting onto W, because we are projecting onto W means the project vector in W. This means that P lies in the span of the vectors. The P lies in the span of the vectors u1, u2, and so on un. That is what that means. That is, say P lies in the span of this vector means we can write P equal to some scalar multiple of these vectors. Suppose I am taken x1 cap u1 plus x2 cap u2 and so on xn cap un. This one you can write. Okay, better to write this way. See, now this one you can write u1 x1 cap plus u2 x2 cap and so on un xn cap. This is same as u1 u2 we can write in a matrix a into x cap, where x cap is n-dimensional vector. N-dimensional vector. The same that means we write p equal to a x cap. Now from second equation, see if write a transpose v equal to a transpose p. Now what the p here? Now from equation 2, now substitute here p is p equal to x cap. That means a transpose v equal to a transpose a x cap. This is the one. So now if we find out x cap, we can find the p, because p equal to x cap. We know a is, if we know x cap, then we know x cap as, because a is columns of uis. See, this one the equation. See, this is the one. Suppose take a transpose is v equal to a transpose a. See, a transpose v, there v, a is knowing what, v is the no one. If we all are know, we can find, solving this equation we can find x cap. Solving this equation. See, in other words, suppose we want to find x cap. If we square now this one, suppose if a transpose a is invertible, it's always invertible, because a transpose a is invertible. Just I give reason why it's invertible. Where a is the n by n matrix. See, m by n matrix, there are m linearly independent columns. The rank is m. Rank is m. What about a transpose a? What the rank? What the matrix? A transpose a. A is n by n. This is the n by m. That means we get n by n matrix. Wait, this is oh, A is n by m matrix. N by n matrix. A transpose is m by n matrix. That means A transpose A is m by m matrix. The rank is m. This A transpose A. They are linearly independent. This A transpose A rank is also m. That means A transpose A is invertible because A is the m linearly independent column vectors. That's why A transpose A is invertible. And you can check it. This A transpose A is always symmetric and invertible. This A transpose A is symmetric and invertible. Now divide with inverse this one. Now, therefore, now we can write x cap equal to x hat equal to A transpose A inverse A transpose B. Let's take third equation. Since A transpose A is invertible, just now I given reason why it's invertible. It's invertible, we can write this one. Now equation 3, yeah, now from here you can find x hat. If you know x hat, you can find the projection. Now we are finding a projected vector. So now how to find a projection matrix? See now, mm, so now multiplying equation 3 with A, we get A. You can write multiply A into A transpose A inverse into A transpose V equal to A x hat. This is same as P. That means, therefore, that means Ax hat is the small p. Here, capital P equal to A into A transpose A inverse into A transpose is a projection matrix. Is a projection matrix. By using this projection matrix also we can find the orthogonal vector. That is therefore the projection matrix. Therefore, that is small p equal to projection matrix into V. By using this also we can find the orthogonal projection. That means P, by using this derivation, P capital V, the projection map, by about derivation, the projection matrix P maps a vector V belongs to Rn into onto map to orthogonal projection or orthogonal projection, small p equal to capital P V in the subspace. W. Yeah, this is the one. So now remember this is the projection matrix P equal to A into A transpose A whole inverse A transpose. So now observe here, this is the one P is a subspace. So this is a projection matrix. We are finding the orthogonal projection or projection simply. This small p and capital P. Capital P we write projection. So now already we know this projection matrix is, we know capital P is not, you can write this is a P transpose P, and second one symmetric and it's idempotent. You can check it. But here rank is not 1. Previously only one column is rank is 1. But if it's a rank depending on number of columns, how many columns are spanning a subspace. If n columns are spanning subspace, that rank is n. If 2 columns, rank is 2. So it is always, the projection matrix always symmetric and idempotent. This is the one. See now observe here, if whatever in a plane, see, suppose we are projecting vector P, whatever you are projecting V onto this one, this is error vector. This all are right angle triangle. This one. So now observe here, we are finding this one. Uh, this keypad. See now you can go for like previous one, just in one dimensional. One dimensional we are writing projection matrix is the U transpose by U transpose U. That same as the, see now here you can write, now same it's one. In place of U is A. That A transpose, this is the inverse. A transpose A inverse and A transpose. That means same thing this one. This is the one dimensional. One dimensional means it's a line. That we get same thing. This is a projection matrix in one dimensional. This is the n dimensional or n whatever. More than one dimensional. See now we got. See now observe here. See what are the equation we are getting? A transpose V minus P. That means A transpose. Now observe here this key point. A transpose V minus P. That same equal to 0. That means A transpose V minus P means AX hat equal to 0. This dot product A transpose and V minus AX hat equal to 0. Already we discussed rows fundamental four subspaces. When that see when that A transpose X equal to 0, what the A transpose X equal to 0 means? This is solution set is left null space. Left null space. This exists. Now here that means here this V minus AX hat lies in is left null space. Left null space. Left null space of A or null space of A transpose or null space of A transpose. Left null space or null space of A transpose. This one. See now already you know this because we are since A is the column space. A is column space. Column space and null, some number column space and that vectors are perpendicular means this is the left null space. Since A is column space. Column space. Therefore, this V minus X hat is the left null space of A. You know this is the column space and the left null space orthogonal. You know column space and left null space are orthogonal. Yeah, that's the thing. Yeah, that means this A transpose V minus X hat is the in the left null space. This is a solution set of left null space V minus X hat. Now we'll see some examples. So now we can find anyways. Suppose you see like if A equal to 1 1 1 0 1 1 and V equal to 2 0 0, then find X hat small p and capital P. If somebody ask me like this, how to find this one? We know X hat. We have to find X hat. Anyways, so now we see observe here this one. A transpose B equal to A transpose A X hat. Yeah, that means now use that relation. Second, this relation. Now you can use this relation. A transpose A X hat equal to A transpose X hat equal to A transpose B equal to A transpose. So now using this one you can find X hat, or you can find X hat equal to A transpose A inverse into A transpose B. You can find anyway. If you know X hat P equal to A B, and capital P is the projection matrix. That's all. Solution. Now you have to find this one. Now given A is this one. Now first find the A transpose A. What the A transpose A? 1 1 1 0 1 1 into 1 1 1 0 1 1. This is equal to, you get 2 by 2 matrix. 1 1 1 3 2 2. It's always symmetric matrix 2. This is the matrix. You can use this relation or and this relation. A transpose V. A transpose V equal to 1 1 1 0 1 1 2 0 0. This is equal to 2 plus 2 2 0 0 0 all are 0 2 0 this one. So now therefore now we have to take A transpose A x hat. That means let x take x hat equal to x1 x2 hat. So now A transpose A x hat equal to A transpose, that implies, see now 3 2 2 2 x1 hat x2 hat equal to 2 0. Solving this equation by using any method, this implies, that means 3 x1 hat plus 2 x2 hat equal to 2 and 2 x1 hat plus 2 x2 hat equal to 0. That means x1 hat equal to minus x2 hat. Therefore x hat equal to this x1 hat x2 hat. What will get? X1 equal to minus x2. If substitute here, if x1 equal to minus x2, that means or x2 equal to minus 2, that x1 equal to 2. Is it correct? Suppose substitute x2 equal to x1. x2 equal to x1, that x1 equal to 2. x1 equal to 2 for x1 hat equal to 2 and x2 hat equal to minus 2. This one we are getting. You can use this one. You can take inverse and this one. This is x1 hat x2 and p equal to now projection. This projection or orthogonal projection, p equal to AB. AB means A is the 1 1 1 0 1 1 into V. V is x hat. X hat is 2 minus 2 2 0 2 minus 2. This one we are getting. I did any mistake? 3x1 plus x2 is x1. Substitute here, x1 equal to 2. Okay. So now, what the error vector? This error is v minus p. V minus p. This error always perpendicular to this column space. V minus p. V is the 2 0 0 0 minus p 2 0 0. This is null vector, 0 vector. Already you know 0 vector is always orthogonal to every vector. That's why this is, there is no, we are getting exactly projection. That is exactly shadow, there is no error. See, now we find projection matrix. Now we get error is 0 0. That means that shadow get exactly. But the projection is exactly, there is no error. See now, projection matrix. Matrix P equal to, what the A transpose A inverse into A transpose. So this is equal to A into A. A is the given matrix 1 1 1 0 1 1. A transpose A. A transpose A, this inverse 1 over 6 minus 4 2 into it's a 2, it's minus 2 minus 2 3, inverse of that matrix 2 by 2 matrix. So 1 1 1 0 1 1. So now multiply this one, you can write 1 by 2 outside. You can go multiplication left side to right, right to left, whatever. 2 0 2 2 minus 2 0 2 minus 2 0 minus 2 0 minus 2 plus 3 1 minus 2 plus 3 is 1. This one is equal to 1 by 2 into 3 by 3 matrix, because it's a R3 space, you get 3 by 3 matrix. 1 this one 2 0 2 1 0 2 0 yeah 2 okay right 2 0 0 1 0 0 0 0 0 0. Now 2 minus 2 0 0 1 1 0 1 1. 2 minus 2 0 0 into 1 1 to 1 1. This is the projection matrix. It's a symmetric. You can check it p transpose p square also p itself. This one. Now observe here the projection. Now projection of now V onto column space of A, column sub A is small p equal to capital P into V. Now see 1 by 2 into 2 0 0 0 1 1 0 1 1 into 2 0 0. It must be V is 2 0 0. It must be same itself vector. See now you can check 1 by 2 into 4 0 4 0 0 0. That means get 2 0 0. Get same vector itself. That projection is itself. There is no error. Itself we get same projection. This is one of the example. Now we'll see another example. Suppose example 2. Suppose we'll see find the projection matrix P for the two-dimensional subspace W of R4 spanned by the vectors 1 1 0 2 and minus 1 0 0 1 1. Now what is the orthogonal projection of the vector 0 2 5 minus 1 onto W? This is the problem. Suppose in that one, if it's given transpose or not, we have to consider the column vector. Sometimes may I mention transpose, or sometimes may not mention. That's the column vector. That solution. See now we have to that projection. We have to put a projection matrix. It's two-dimensional subspace. It's spanned by two vectors. First, to write it in the matrix form. Let A equal to write in the whatever given vector, row vector, column vector, whatever, write column vector 1 1 0 2. Must write in column vector minus 1 0 0 1. So now what about A transpose A? We require A transpose A. Now find the A transpose A. Okay, right 1 1 0 2 minus 1 0 0 1. Sorry, A transpose A. A transpose 1 1 0 2 minus 1 0 0 1 into A. 1 1 0 2 minus 1 0 0 1. This is equal to, we'll get 3 by 2 by 2 matrix again. 1 1 0 4. 4 plus 1 plus 4 by 6. Okay, next minus 1 0 0 2. Minus 1 plus 2 is 1. Minus 1 0 0 2 1. It must be get symmetric matrix. 1 0 0 1. That's a 2. This is the A transpose A. Therefore, projection matrix, the projection matrix P equal to, what is the A into A transpose A, inverse into A transpose. Now this one A is this matrix 1 1 0 2 minus 1 0 0 1. A inverse, you can find A transpose A inverse is 6 minus 1, 1 by 11 into 2 minus 1 minus 1 6. This is the one. This is the 1 by 11 into 2 minus 1 minus 1 6 into A transpose. A transpose is the 1 1 0 2 minus 1 0 0 1. Now multiply this matrix, we will get 1 by 11 into 4 by 4 matrix. 10 3 0 minus 1 3 2 0 3 0 0 0 0 minus 1 3 0 10. This is the one. Now what is the projection? The orthogonal projection. Now orthogonal projection of 0 2 5 minus 1 onto W. That is, now multiply this one. 1 by 11 into this vector, we will get 1 by 11 into 7 1 0 4. You can check it, this one. Okay, right. Is small p equal to capital A into vector. Suppose we are taking this as a vector V. No, capital P into V. Multiply 1 by 11 into 10 3 0 minus 1 3 2 0 3 0 0 0 0 minus 1 3 0 10. Multiply this one with vector, what the vector? 0 2 5 minus 1. So this one will get 1 by 11 into 7 1 0 minus 4. This is the vector projection. Now you can check it. If it find the error vector must be orthogonal to each column of the this given space. You can check it, that one. See, one more condition, this one. See, now we are what we are writing, projection matrix is the A into A transpose A inverse into A transpose. Suppose you are split this A inverse, what will get? A inverse transpose into A transpose. That means A into A inverse. This one can write A inverse transpose into A transpose. So A into A inverse, one identity will get. Means we get projection matrix is identity. Is it true? But it's not possible. The projection matrix may not be identity. See, why it's getting? See, we are splitting this one, A transpose A inverse. See, but here A is, it's not possible. It is not possible. The splitting not possible. Because where A is not a square matrix. A is not square matrix. It's not a square matrix. That means the splitting is not possible. Don't do like this. Don't split. If you split, you get identity. Because it's not possible to split one. Because it's not a square matrix. It's a rectangular matrix. If it's square matrix, that's the possible. The identity matrix, projection matrix is the identity. One more thing. See, we are writing projection equal error equal to V minus P. That means P we are writing, we can write V minus V equal to, we can write P minus P plus E. That means the orthogonal vector we can split to two, projected vector and error vector. The vector we can split to two. projected vector and error vector. Now another example, we'll see. Compute the projection of the vector v110 onto the plane x plus y minus z equal to 0. Now you have to find the projected onto the plane, this plane. See, how to find this one? First plane, write a subspace. Here, the plane is generating a subspace. Now subspace is solution. First write subspace. Subspace W equal to, what is the subspace? X, Y, Z in the 3-dimensional. Such that x plus y minus z equal to 0. This one can write x, y, you can write z equal to x plus y. Such that x comma y belongs to R. That means we can write this is the, if take on x is 1, 0, 1 plus y into 0, 1, 1. So that x comma y belongs to R. So that is therefore W is spans by the vectors 1, 0, 1 transpose and 0, 1, 1 transpose. This is a transpose. If right or not, you have to take the column vectors. Generally we get right transpose, whatever. Therefore A equal to, write in the column vectors 1, 0, 1, 0, 1, 1. Now go for the same procedure like previous. Now we can find the projection matrix and projected orthogonal projection. See, now try another example. Okay, the third, fourth one. Compute the projection matrix P for the subspace W of R4 spanned by the vectors 1, 2, 0, 0 and 1, 0, 1, 1. Also find projection of the vector 1, minus 2, 2, 2. Find projection of this vector also. See, it's not mentioned transpose means you take, that's a column vector, don't take row vectors. We are taking the column space, we are projecting the column space. Okay. Yeah, after that one you can check the answer with that error vector must be orthogonal to each column of that subspace, the column vector. If whatever you write vector matrix A, that error vector must be orthogonal to column space of A. Now I stop here. Thank you.